Hello, welcome to this series of videos dedicated to music theory. With them, we hope to familiarize you with the fundamental concepts that will allow you to understand the way in which musical compositions are structured and prepare you for learning instruments to play them. In your journey along the path of music, you will find many satisfactions, because, as Plato said, music is the essence of order and elevates all souls towards the good, the just, and the beautiful. But this path may seem arduous at times, since, as Jean-Philippe Rameau said, music is a science which must have established rules. These rules must be derived from an evident principle, and this principle cannot be revealed without the aid of mathematics. The notes that are used in the creation of music can be represented by sinusoids. Therefore, it is convenient to start this series of videos dedicated to the theory of music by describing the way in which these functions can be generated. We will begin our exposition by a purely geometric approach in which we have a point that rotates with a uniform circular movement over the circumference of the circle. In the figure shown, the location of this point is fully specified by the unit radius r that links this point with the origin and the theta angle that forms this radius with the x-axis. As this point progresses on the circumference, our interest will focus on the projection sinus of theta of this radius on the y-axis. We will extend this projection to the Cartesian coordinate system located on the right, in which the horizontal axis corresponds to the theta angle and the vertical axis corresponds to the same y-coordinate used to draw the circle. The point starts its path on the circumference at theta equal to 0 and rotates counterclockwise. Note that you have zeros for theta equal to multiples of pi, maxima for theta equal to half pi, 5 half pi, etc., and minima for theta equal to 3 half pi, 7 half pi, and so on. In the study of sound waves that we will discuss in the following video, it is important to remember this fact. The motion of the point on the circumference involves not only a sweep of the angle theta, but also the distance it travels on this circumference and the advance of time as the point makes this journey, so that the point travels a distance equal to the length of the circumference, which we will call lambda, and a time interval t, which we will call period. In the study of sound wave propagation carried out in the following video, it is more convenient to consider the sinusoidal motion in terms of these variables. Next, we will show the representation of the projection of the position of the point as a function of its path s on the circumference. Note that we have zeros for s equal to multiples of half lambda, maxima for s equal to 1/4 lambda, 5/4 lambda, and so on, and minima for s equal to 3/4 lambda, 7/4 lambda, and so on. Next, we will consider the representation of the projection of the point position as a function of time. Note that we have zeros for t equal to multiples of half the period, maxima for t equal to 1/4 of the period, 5/4 of the period, and so on, and minima for t equal to 3/4 of the period, 7/4 of the period, and so on. The above was limited to sinusoids as a function of a single variable. Now, in their trajectory from the source to the listener, sound waves have variation in space and time. For a pure tone, such as a note of a musical scale, we can incorporate these variations with the distance and with time already visualized in a single function of the form, in which we have defined the wave number k and the angular frequency omega. For a given wave, the wave number indicates the number of wavelengths per meter, and the angular frequency the number of radians per second. For the pure tones found in our musical studies, the definition of the frequency f is of the utmost importance. Below is the animation of a pressure wave resulting from the emission of a pure tone. The point located at the intersection of the rising part of the wave with the x-axis is a good reference to observe its motion. To this point, or to any other point of the wave, For example, a point on its positive crest, it takes a time of 1 period to travel a lambda distance. Therefore, the velocity of the wave is. Thank you for watching this video. In the next one, we will use the expression for the traveling wave to produce an animation to give you an idea of how a pure tone is produced by imparting a sinusoidal motion to a rigid plate.